Chapter 13, Sample Problem Number 4. A frictionless cart of mass m is attached to a spring with spring constant k. When this cart is displaced 6 centimeters from its rest position and released, it oscillates with a period of 2 seconds. 4 students are discussing what would happen to the period if the original cart with mass m was displaced 12 centimeters from its rest position instead of 6 centimeters and then released. Aiden says the spring is stretched more, the force will be greater, causing a greater acceleration and greater speeds overall. Since the cart is moving faster, the time will go down, probably to 1 second since the force is doubled. Barb says the cart has further to go now, and so it's going to take longer to make a complete cycle. It's going to go farther on both sides of the rest position, so the round trip is 48 centimeters instead of 24 centimeters. The period is going to double. Charles says the cart has 4 times as much energy, and the conjugate variable for energy is time according to the Heisenberg uncertainty principle. The energy quadruples when the spring stretch is doubled, so the time must only be 1/4 as much. The period will be 1/2 second. And Dallas says stretching the force twice as far means k is twice as big, and since the period is 2 pi times the square root of the spring constant divided by the mass, doubling the spring constant and leaving the mass alone is going to double what's inside the square root. And if we take the square root, we're going to get a period of 2 seconds times the root of 2, or 1.414 seconds. Let's go through these one by one. Since the spring is stretched more, the force will be greater, says Aiden. That's true. Causing a greater acceleration, that's true, and therefore a greater average speed, greater speed overall, also true. Since it's moving faster, the time will go down, probably to 1 second, because the force is doubled. And while this statement is true, and that statement is true, what Aiden misses is that this actually doesn't have to be true, because the distance has also changed. So although the average speed is higher, the distance to be covered is also much higher, and so those effects could conceivably cancel out. And we'll come back to Aiden at the end. Barb says the car has further to go now. That's certainly true, and it's going to take longer to make a complete cycle. This is a problem, actually, because by saying that right here, she has assumed her answer. So we really should just neglect that. That's a statement of the answer. If you say going further means the time is longer, then you've already said that the period will change. And so the rest of this becomes nonsense. But really, she's begged the question, and we can't do that. We have to go back and say, look at the rest of her statement. It's going to be farther on both sides of the rest position. That's totally true. So the round trip is now 48 centimeters instead of 24 centimeters. So the period will double. And this is, while these statements are true, we have the same problem that we have with Aiden, which is that does not necessarily mean that the period will double either, because the speeds are higher, so we don't have the interplay directly here. All right, Charles says that the cart has 4 times as much energy. That's fair. The energy is 1/2 ka squared. If we double the amplitude, we quadruple the energy. And it is even true that the conjugate variable for energy is time according to the Heisenberg uncertainty principle, but really one has to wonder what's going on there. This is not a quantum mechanical system, so it's kind of strange that you would even bring in the Heisenberg uncertainty principle, and so it's just not relevant in a classical system. There's more going on here. Also, the conjugate is about uncertainties in energy, not the energy itself. So even in the Heisenberg world, even in the quantum mechanical world, you would not get any kind of relation that says the absolute time and the absolute energies, only their uncertainties. And finally, Dallas, stretching the spring twice as far means k is twice as big. Well, Dallas goes right off. K is a function of the spring, not of the system's arrangement. K is explicitly not changing because we're not changing the spring. So this statement is just not true, and that kills everything here. Also, it's not a good day for Dallas, because also this is actually not true either. The actual period relation for simple harmonic motion is twice pi times the root of m over k. So Dallas has that flipped, and therefore is going to be wrong no matter what comes out. So what we end up with is that, in fact, none of the students have correctly seen what's going to go on. What actually happens is no change. The amplitude is irrelevant to the periodicity of a simple harmonic system. It depends only on the inertia term and the restoring term. It doesn't depend on how big the system is. What went wrong for Aiden is that although it goes through a greater distance, it goes through a greater distance and has a greater speed, and those two effects essentially obviate each other. So we end up with only that the mass and spring constant matter.